Hi there, folks. Today we're looking at patterns, equations, and graphs. And the first thing we're going to look at is the idea of having an equation that has more than one variable in it. All right. So an equation with two variables, x and y, if we have both of those variables present, a solution is in the form of an ordered pair where it's x and then the y value. So x comma y. All right. And it's important to remember that ordered pairs are always the x value followed by the y value. And a solution is basically an ordered pair then that makes the equation true. So an x and a y value that satisfy the equation and give us a true statement. For example, if we look at something like this guy, it just says, hey, we want to know, is this ordered pair one of the solutions to this equation? And the thing about equations with two variables in it is there's multiple solutions. There's typically an infinite number of solutions, really, but they're all very specific solutions. And so we want to determine, is this ordered pair one of those solutions, okay? And so, for example, if I look at something like this guy, I'm just going to plug them in. Remember, the 3 goes in for x, and the 10 goes in for y. And I just simplify, see if I get a true statement. Here I get 10 equals 12, which is ridiculous. That's a false statement. So the answer here is no. But even so, just knowing that this thing is no, it still tells us something about this guy. And so the follow-up question here is, can you think of an ordered pair that would be a solution for this equation? And hopefully you're looking at this going, well, when I plugged the 3 in, the value that I got was 12. So the ordered pair 312 would also be a solution, okay? And you could pick other values for x and get values for y, and that ordered pair would also be a solution. So understanding that there are multiple solutions here, there's an infinite number of ordered pairs that would work for this particular equation. If I look at something like this guy, again, we're going to plug it in. So I plug the 3 in for y, I plug the 2 in for x, and I get 4 minus 1, which is a 3. So this one, 3 equals 3, that's a true statement. So the answer here is yes, this one is a solution. But now, again, a follow-up question to that, even though that's a solution, remember there are more solutions. So can you think of another ordered pair that would also be a solution? And so the idea here is, yeah, just plug another value in. Maybe plug something like a 3 in for x. And if you were to plug a 3 in for x, well, 3 times 2 is a 6, minus 1 is a 5. And so that would be a solution to this thing. And again, you could have picked any x value, plugged it in, and gotten a y value. But that idea that that ordered pair is a solution to the equation, all right, there's an infinite number of ordered pairs on this line, so there's an infinite number of possibilities for ordered pairs that work, okay? Using a table, tables, equations, and graphs, the relationship between two variables can be expressed in any one of these different ways. And this is kind of where we're heading. You've probably done some of this before, but the idea that we want to express these things not just with equations, but we want visual representations of these things, okay? We want graphic type of organizers like a table that can show us the relationship between these things. For example, if I were to consider this example, all right, Jack is 2 years older than his sister, Jill. How can you represent the relationship between Jack's age and Jill's age? And so the first thing we have to do is we have to start representing things like Jill's age, all right? And so Jill, we don't want to start with something like -2. That wouldn't make any sense. She can't be -2 years old. So maybe I'll start here with something like 1. And it says Jack is 2 years older than his sister. So if Jill is 1 year old, how old then essentially is Jack? And the answer would be 3 years old because he's 2 years older. So let's say she becomes 2 years old. Now, how old is Jack? Well, he's 2 years older, so he's 4 years old. Okay? And you could keep going when she's 3 or 4 or 5 or 6. And so he's always 2 years older if I tack an extra 2 on there. And so it ends up looking like this. So we can see that relationship of Jill's age increasing and Jack's age increasing. And we can see that his age is always 2 more than hers. Okay? But then there are other patterns within this that we're going to want to look for. Okay? And so the table, yeah, it expresses that relationship of 2 years older, but it shows us other patterns that exist within that relationship. okay? So if I were to take this a step further, so again, here's that same table we were just looking at. It's all filled in. The idea here is we want the relationship in terms of the pattern when we look at Jack and Jill, all right? And so if we look at like Jill, her age is going up by 1 each time, and that in and of itself is a pattern. The fact that this is going up by 1, that is a mathematical pattern, okay? And then the idea here also is that Jack's age is also going up by 1, all right? And the thing about this is we want to express this in different ways. See, previously we had an equation that we were plugging stuff into. Now I'm going to want to write an equation, all right? And we want to write an equation in terms of x and y that utilizes these ordered pairs. So if we think of this kind of as ordered pairs, you know, that first one is the ordered pair 1, 3, all right? And essentially we're just using Jill's age as the x and Jack's age as the y. The next one would be the ordered pair 2, 4. And then 3, 5, and then 4, 6, and so on and so forth. And I could keep this going. Okay? But now I want to write an equation. And so we want to think about it this way. The equation is y equals, all right? We always kind of want to start with that y equals, but now we want to describe that in terms of x. And some of the things that can help us here, well, the pattern in terms of y is that it's going up by 1 each time. See, we're adding 1 each time. When you add something over and over again, I don't know if you remember this from elementary school, but that's multiplication. That's what multiplication is. Like multiplying by 5, like 3 times 5 means that you're adding 5 3 times, okay? Multiplication is just doing addition a bunch of times. So if I'm adding 1 over and over and over again, it means I'm multiplying by 1, so it's like a 1x. See, I'm multiplying 1 times x. But now the other thing that we look at is if I were to plug this first x value, and if I plugged the 1 in here, 1 times 1 is 1, well, I'm supposed to get a 3. So I'm 2 off, I have to add 2. And that goes back to the relationship between Jill's age and Jack's age, is that he's 2 years older. So if x is Jill's age, all right, I have to add 2 to get Jack's age. And so we kind of see those two things come together when we look at the equation, all right? But that multiplier comes from the pattern of Jack's age. And then the fact that they're 2 years apart is what tells us what to add that to, okay? And then in terms of the graph, if I was just going by ones here on the graph, so I'm just going to plot each of these ordered pairs. So the first one, let me scroll down a little bit. The first one is the ordered pair 1, 3, so 1, 3 is right here. The next one, 2, 4. The next one, 3, 5. The next one, 4, 6. 5, 7. And the idea here is, yeah, I could go back up to that table and plot every ordered pair that I see. But again, we want to look at this from a perspective of looking for a pattern. And visually, when you look at this graph, when you look at those points, okay, the pattern is that we're going up 1 and over 1, and then up 1 and over 1 again, and then we keep that pattern. If I continued this pattern, I'd get a point here, and here, and here, and you'll find that those correspond to the ordered pairs that I have from my table, okay? And they even reveal more than what I had in the table, like that extra point that I plotted right here. That's telling us that Jack was 2 years old when his sister was born, okay? So essentially when she was 0 years old, all right? And so again, we're expressing this in different ways. The graph can only take, the table can only take us so far, but now the graph shows us visually what that pattern looks like, okay? If we look at something like this guy, notice I have this, this block of tiles, and then I have 2 blocks of tiles, and then 3 blocks of tiles. Continuing the pattern, I would have 4 blocks of tiles left, but we want the relationship between the blue tiles and the total number of tiles, okay? So in the first scenario, I have 1 blue tile. That's right here. So when I only had 1 of those blocks of tiles, I had 1 blue tile, but there are 9 total tiles. And now when I go to the next piece of the pattern, right here, there are 2 blocks of tiles, and see there are 2 blue tiles, but there are 18 total tiles. And then next, we're looking at this guy. Now there's 3 blocks of tiles, which means I have 3 blue tiles, but I have 27 total tiles if I were to count them all up. And so the idea here is, okay, we can see that there's a relationship between the blue tiles and the total tiles, but now we want to look for other patterns. Like when we look at the blue tiles, the pattern is we're going up by 1 each time, adding 1, adding 1. So if I kept that pattern going, it would be a 4, then a 5. Okay. If I looked at the total tiles, think about what the pattern is: 9, 18, 27. It's going up by 9 each time. So the next one would be 36. After that would be 45. And we could keep this going kind of indefinitely. I could keep going 6, 7, 8, right? And I would keep going up by 9s each time here: 54, 63, 72. All right. So the idea here is looking for patterns beyond just the relationship between the blue tiles and the total tiles. And now, once again, if I wanted to find out something beyond this, like maybe I want to go all the way out to 8, which I kind of already did. I showed it on the table there. But let's say I wanted to go out to 100 or 1,000. All right, I don't want to extend the table that far. This is where equations are a good way to express this thing. And so here I got to figure out the relationship. Well, again, just like before, the pattern here is going up by 9 each time. If I keep adding 9 over and over again, that's like multiplying by 9. That's what adding 9 over and over again is. So it's y equals 9 times x. And if you kind of check that, if you like plug a 1 in there, you get 9. If you plug a 2 in, you get 18. If you plug a 3 in, you get 27. That's the relationship between these two things, if you look at this as x and y. Okay? And so algebraically, if we want to use the equation, we'd say, oh, y equals 9 times 8. And what I get is y equals 72. And that's the ordered pair that we discovered right here. Okay? 8 comma 72. When I plugged an 8 in, I got a 72 out. And yeah, the table was easy enough to extend to get that value. But if I wanted like the 100th value, I want to know how many total tiles are there when there's 100 or 100 blue tiles. Well, I certainly wouldn't want to extend the table that far. That's where equations come into play. Okay, so we're looking at the relationship in terms of a table, and then we're coming up with an equation based on the patterns we see within that table. Okay.